I'm here to discuss my submission to the data-driven folks on the dengue AI predicting disease spread. Uh, this is a PowerPoint presentation and there will be a narration associated with it. And obviously, if you have any questions or comments, feel free to email me in the usual way. Discussion about dengue fever and why it's an area of study. It's prevalent in most countries that are at or near the equator. It's transmitted through mosquito bites, and there's actually two types of mosquitoes that transmit the disease. And there's a lot of uncertainty on the actual number of cases per year. There's about 50 million documented cases, and estimates are they could be as high as 500 million cases per year. And the reason is that many of these cases are very mild and don't require any kind of medical treatment. In most cases, the symptoms go away in 5 to 7 days, but there is a roughly a 2 to 4% mortality rate based on the 50 million cases per year. It has increased rapidly in the past 50 years. And the challenge from the data-driven people are to use open data to predict the occurrence of dengue based on climatological data. My approach to the problem is multi-step. There is a literature review, then look at the data and understand any correlations within the data after I clean it, and then a graphical analysis to identify any key trends or thoughts. Then I subset the data for regressions and time series, and I'll go into a little bit of detail on how I subset the data. And I actually ran five models to determine the best fit, evaluating performance, and I've got a summary of that, and then submitted it to data-driven for scoring. And the label data, which is included in the label format. So I needed to add the total cases column to both the training and the test sets. There are many different ways of looking at correlations, and a common method is a heat map. But with all the data elements here, it was very difficult to interpret. So I did find these charts in the Coregram functionality, and I think it's a bit easier to read, and they have the actual names of the data elements up in along the side here. You can barely see it, but using this approach, you're able to look at the key relationships, and the dark blue or the dark orange are the key relationships. Total cases is the bottom row. So if you go across the bottom row, you can identify these key relationships, and then I listed these relationships down below. There's some pretty neat charts you can get from the data provided, and you can see in the farthest chart on the left, total cases by week. So it's fairly level, but it does tend to peak and escalate in weeks 35 to 45, and you can see the bubbles up toward the top there. And the average temperature I found fascinating. So the temperature range for when you see the most cases is somewhere between 27 and 29 degrees centigrade. And under 24 degrees, you rarely see cases, and over 29 degrees, you rarely see cases. So there's a period at which the mosquitoes thrive, and they don't thrive when it's either too hot or too cold. And similar to the dew point. So the dew point is a combination of temperature and humidity. And you could see, again, it starts out fairly low at around 292, but when it gets up around 296, 297, dew point is high combination temperature and humidity. You can see that the number of cases accelerate fairly rapidly. The time series analysis is kind of interesting, and you have to be careful here looking at the SJ San Juan data and the IQ Iquitos data. because the dates are different. So even though the graphs are under one another, the time frame is different. So the SJ data starts at 1990, the IQ data starts in 2000. And you can see that the data is slight, very, very slight downward trend in San Juan and a slight upward trend in the IQ data. The data is seasonal, and you can see that through the decomposition graphs, seasonal in both. Again, the Iquitos data is slight upward trend, while the San Juan is level or slightly declining. And then you can see the random spikes. You see that both in the time series graphs and in the decomposition. And the spikes are not necessarily in the same time frame because the climate conditions in South America and Puerto Rico are different. So I broke out the San Juan and Iquitos data, create subsets, and then even though there was a test set given, I wanted to create a separate training and test sets within the training set. Did that for modeling purposes and to determine the best model. So actually working with a test set which I created and used that to feed the test set which was given to us. And I used that to identify the best models. So I did my analysis on the training set and then took the best models and applied them to the test set, which we used for submission. The seasonal ARIMA model was actually my best model, and I'll show you the results in a few minutes. But it helps deal with the seasonality, which was prevalent in the data. So you can see on the left-hand side, which is the San Juan data, you can see the seasonality, and you can see the model that was used. What's not showing there is the seasonal data, 112, and then 000. In the graph on the right, you can see a slightly different model. So again, I derived this from working with the separate training and test sets within the training set. And that's a 012 with a 001 model. So here's a look at the different models. Here's the ETS model. And you can see that their primary means of scoring is MAE. And the San Juan data had an MAE of 32, and the Iquitos had an MAE of 11. You can see the variability leading up to the forecast, and the forecast is primarily a straight line, which you'll see later. I have a chart on this. I thought that Garch produced the neatest charts there, and I had to dig around online to find the right code to get these graphs, but they're kind of neat, and they do show the variability in the data, and they do show the forecast in a little different manner. So San Juan produced fairly tight MAE of 8.65 and Iquitos 3.41. I found Garch to be a little difficult to work with because it doesn't have the same functionality as the Heinemann programs. But here's the results and the confidence intervals. Again, the incidence of cases is much lower on the Iquitos side, and there's a smaller population. But the forecasts do follow the same pattern. Okay, did a set with the XREG model, and there I used the data from the correlation analysis to plug it into the XREG function in ARIMA, and you can see the results here. It shows a different forecast pattern. It's not a straight line here. It's an ascending line in both, with a little bit more variability in the IQ, the Iquitos model, and you can see they both produce fairly low MAE, an 810 for San Juan and a 397. I had some fun with the NNet model. And you can see the extreme variability and the randomness there. The NNet model seems to pick that up, especially noticeable in the San Juan submission, and you can see the forecast goes up and then down and back up again, which is the way the data looks. So San Juan had an MAE of 22.3. Iquitos, the forecast drops off and then levels out. And that had an MAE of 8.1. So sometimes I think we get hung up on all the metrics around the appropriate model and which one we should use. And I find it's helpful to graph the actual forecasts over time. And you could see that the ARIMA and the GARCH and the ETS, the graphs are fairly similar. The forecasts are fairly similar. And they have a very, very similar pattern. Matter of fact, the ARIMA overlays the ETS forecast. But the blue line is the NNet forecast, and it looks more like the underlying data for San Juan. It's kind of a stair-step pattern for Iquitos, and you see the cyclicality in the XREG forecast moving up and down, and on the IQ you see it again in a stair-step fashion. So here's the big finality, the big final, and to summarize the RMSE, the MAE for each model, and the score that I received from Data Driven. And you can see that the seasonal ARIMA model actually had the best results, and it came in at 29.24, and most of the other ones clustered between 30 and the mid 29s. So the ETS came in at 29.90, the GARCH came in at 29.90, the XREG came in a little bit lower at 29.66, and the NNet came in at 30.25. So the NNet, the graphs seem to be more reasonable, and also when you look at the ACF and the PACF, looks pretty good. So all the results were similar, and this resulted in an overall score of around 980 out of over 3,000 submissions. I wish it could have been higher, but I thought it was a good exercise and a good result. So again, any questions, you can email me, and I'll get back to you as soon as I can.